b. Restoring the continents to their pre-drift positions creates a single glaciation centered on the South Pole and puts the coal swamps near the equator. Figure 2.7 Full alternative text description. Wegener suggested a more plausible explanation for the late Paleozoic glaciation. The southern continents were joined together in the supercontinent of Pangaea and located near the South Pole. This would account for the polar conditions required to generate extensive expanses of glacial ice over much of these landmasses. At the same time, this geography places today's northern continents nearer the equator and accounts for the tropical swamps that generated the vast coal deposits. As compelling as this evidence may have been, 50 years passed before most of the scientific community accepted the concept of continental drift. The Great Debate. From 1924, when Wegener's book was translated into English, French, Spanish, and Russian, until his death in 1930, his proposed drift hypothesis encountered a great deal of hostile criticism. The respected American geologist R. T. Chamberlain stated, Wegener's hypothesis in general is of the footloose type, in that it takes considerable liberty with our globe, and is less bound by restrictions or tied down by awkward, ugly facts than most of its rival theories. One of the main objections to Wegener's hypothesis stemmed from his inability to identify a credible mechanism for continental drift. Wegener proposed that gravitational forces of the Moon and Sun that produce Earth's tides were also capable of gradually moving the continents across the globe. However, the prominent physicist Harold Jeffreys correctly argued that tidal forces strong enough to move Earth's continents would have resulted in halting our planet's rotation, which, of course, has not happened. Wegener also incorrectly suggested that the larger and sturdier continents broke through thinner oceanic crust, much as icebreakers cut through ice. However, no evidence existed to suggest that the ocean floor was weak enough to permit passage of the continents without the continents being appreciably deformed in the process. In 1930, Wegener made his fourth and final trip to the Greenland ice sheet. Although the primary focus of this expedition was to study this great ice cap and its climate, Wegener continued to test his continental drift hypothesis. While returning from IceMet, an experimental station located in the center of Greenland, Wegener perished along with his Greenland companion. His intriguing idea, however, did not die. Figure 2.8 Alfred Wegener during an expedition to Greenland. Why was Wegener unable to overturn the established scientific views of his day? Foremost was the fact that, although the central theme of Wegener's drift hypothesis was correct, some details were incorrect. For example, continents do not break through the ocean floor, and tidal energy is much too weak to move continents. Moreover, for any comprehensive scientific theory to gain wide acceptance, it must withstand critical testing from all areas of science. Despite Wegener's great contribution to our understanding of Earth, not all of the evidence supported the continental drift hypothesis as he had proposed it. As a result, most of the scientific community rejected continental drift or at least treated it with considerable skepticism. However, some scientists recognized the strength of the evidence Wegener had accumulated and continued to pursue the idea. Concept checks 2.2. 1. What was the first line of evidence that led early investigators to suspect that the continents were once connected? 2. Explain why the discovery of the fossil remains of Mesosaurus in both South America and Africa, but nowhere else, supports the continental drift hypothesis. 3. Early in the 20th century, what was the prevailing view of how land animals migrated across vast expanses of open ocean? 4. How did Wegener account for evidence of glaciers in portions of South America, Africa, and India, when areas in North America, Europe, and Asia supported lush tropical swamps? 5. Describe two aspects of Wegener's continental drift hypothesis that were objectionable to most Earth scientists. Wegener was not the first to conceive of a long-vanished supercontinent. Eduard Suess, a distinguished 19th-century Austrian geologist, pieced together evidence for a giant landmass comprising South America, Africa, India, and Australia. It is important to note that coal can form in a variety of climates, provided that large quantities of plant life are buried. 2.3 The theory of plate tectonics. List the major differences between Earth's lithosphere and asthenosphere and explain the importance of each in the plate tectonics theory. Following World War II, oceanographers equipped with new marine tools and ample funding from the U.S. Office of Naval Research embarked on an unprecedented period of oceanographic exploration. Over the next 2 decades, a much better picture of large expanses of the seafloor slowly and painstakingly began to emerge. From this work came the discovery of a global oceanic ridge system that winds through all the major oceans. In other parts of the ocean, more discoveries were being made. Studies conducted in the western Pacific demonstrated that earthquakes were occurring at great depths beneath deep ocean trenches. Of equal importance was the fact that dredging of the seafloor did not bring up any oceanic crust that was older than 180 million years. Further, sediment accumulations in the deep ocean basins were found to be thin, not the thousands of meters that had been predicted. By 1968 these developments, among others, had led to the unfolding of a far more encompassing theory than continental drift, known as the theory of plate tectonics. Did you know? A group of scientists proposed an interesting but incorrect explanation for continental drift. They suggested that early in Earth's history, our planet was only about half its current diameter and completely covered by continental crust. Through time, Earth expanded, causing the continents to split into their current configurations, while new seafloor filled in the spaces as they drifted apart. Rigid lithosphere overlies weak asthenosphere. According to the plate tectonics model, the crust and the uppermost, and therefore coolest, part of the mantle constitute Earth's strong outer layer, the lithosphere. The lithosphere varies in both thickness and density, depending on whether it is oceanic or continental. Oceanic lithosphere is about 100 kilometers thick in the deep ocean basins but is considerably thinner along the crest of the oceanic ridge system, a topic we will consider later. In contrast, continental lithosphere averages about 150 kilometers thick but may extend to depths of 200 kilometers or more beneath the stable interiors of the continents. Further, oceanic and continental crust differ in density. Oceanic crust is composed of basalt, a rock rich in dense iron and magnesium, whereas continental crust is composed largely of less dense granitic rocks. Because of these differences, the overall density of oceanic lithosphere is greater than the overall density of continental lithosphere. This important difference will be considered in greater detail later in this chapter. The asthenosphere is a hotter, weaker region in the mantle that lies below the lithosphere. In the upper asthenosphere, the pressure and temperature bring rock very near to melting. Consequently, although the rock remains largely solid, it responds to forces by flowing, similarly to the way clay may deform if you compress it slowly. By contrast, the relatively cool and rigid lithosphere tends to respond to forces acting on it by bending or breaking but not flowing. Because of these differences, Earth's rigid outer shell is effectively detached from the asthenosphere, which allows these layers to move independently. Smart Figure 2.9 The rigid lithosphere overlies the weak asthenosphere. Smart Figure 2.9 Full alternative text description. Earth's major plates. The lithosphere is broken into about 24 segments of irregular size and shape called lithospheric plates, or simply plates, that are in constant motion with respect to one another. 7 major lithospheric plates are recognized and account for 94% of Earth's surface area: the North American, South American, Pacific, African, Eurasian, Australian Indian, and Antarctic plates. The largest is the Pacific Plate, which encompasses a significant portion of the Pacific Basin. Each of the 6 other large plates consists of an entire continent, as well as a significant amount of oceanic crust. Notice in Figure 2. 10. That the South American plate encompasses almost all of South America and about 1/2 of the floor of the South Atlantic. Note also that none of the plates are defined entirely by the margins of a single continent. This is a major departure from Wegener's continental drift hypothesis, which proposed that the continents move through the ocean floor, not with it. Watch tutorial, Crust versus Lithosphere. Figure 2.10 Earth's major lithospheric plates. The block diagrams below the map illustrate divergent, convergent, and transform plate boundaries. Figure 2.10 Full alternative text description. Intermediate-sized plates include the Caribbean, Nazca, Philippine, Arabian, Cocos, Scotia, and Juan de Fuca plates. These plates, with the exception of the Arabian plate, are composed mostly of oceanic lithosphere. In addition, several smaller plates have been identified but are not shown in Figure 2.10. Plate movement. One of the main tenets of the plate tectonics theory is that plates move as somewhat rigid units relative to all other plates. As plates move, the distance between two locations on different plates, such as New York and London, gradually changes, whereas the distance between sites on the same plate, New York and Denver, for example, remains relatively constant. However, parts of some plates are comparatively weak, such as southern China, which is literally being squeezed as the Indian subcontinent rams into Asia proper. Because plates are in constant motion relative to each other, most major interactions among them occur along their boundaries. In fact, plate boundaries were first established by plotting the locations of earthquakes and volcanoes. Plates are delimited by three distinct types of boundaries, which are differentiated by the type of movement they exhibit. These boundaries are depicted at the bottom of Figure 2.10 and are briefly described here. Divergent plate boundaries, where two plates move apart, resulting in upwelling and partial melting of hot material from the mantle to create new seafloor. Convergent plate boundaries, where two plates move towards each another, resulting either in oceanic lithosphere descending beneath an overriding plate, eventually to be reabsorbed into the mantle, or possibly in the collision of two continental blocks to create a mountain belt. Transform plate boundaries, where two plates grind past each other without the production or destruction of lithosphere. Divergent and convergent plate boundaries each account for about 40% of all plate boundaries. Transform boundaries account for the remaining 20%. In the following sections we will discuss the three types of plate boundaries. Concept checks 2.3. 1. What new findings about the ocean floor did oceanographers discover after World War II? 2. Compare and contrast Earth's lithosphere and asthenosphere. 3. List the 7 largest lithospheric plates. 4. List the 3 types of plate boundaries and describe the relative motion along each. 2.4 Divergent plate boundaries and seafloor spreading. Sketch and describe the movement along a divergent plate boundary that results in the formation of new oceanic lithosphere. Most divergent plate boundaries are located along the crests of oceanic ridges and can be thought of as constructive plate margins because this is where new ocean floor is generated. Here, two adjacent plates move away from each other, producing long, narrow fractures in the oceanic crust. As a result, hot molten rock from the mantle below migrates upward to fill the voids left as the crust is being ripped apart. This molten material gradually cools to produce new slivers of seafloor. In a slow yet unending manner, adjacent plates spread apart, and new oceanic lithosphere forms between them. For this reason, divergent plate boundaries are also called spreading centers. Did you know? An observer on another planet would notice, after only a few million years, that all of Earth's continents and ocean basins are indeed moving. The Moon, on the other hand, is tectonically dead, so it would look virtually unchanged millions of years in the future. Most divergent plate boundaries are situated along the crests of oceanic ridges, the sites of seafloor spreading. Figure 2.11 Seafloor spreading. Oceanic ridges and seafloor spreading. The majority of, but not all, divergent plate boundaries are associated with oceanic ridges, elevated areas of the seafloor characterized by high heat flow and volcanism. The global oceanic ridge system is the longest topographic feature on Earth's surface, exceeding 70,000 kilometers in length. As shown in Figure 2.10, various segments of the global ridge system have been named, including the Southwest Atlantic Ridge, East Pacific Rise, and Southwest Indian Ridge. Representing 20% of Earth's surface, the oceanic ridge system winds through all major ocean basins, like the seams on a baseball. Although the crest of the oceanic ridge is commonly 2 to 3 kilometers higher than the adjacent ocean basins, the term ridge may be misleading because it implies narrow when, in fact, ridges vary in width from 1,000 kilometers to more than 4,000 kilometers. Further, along the crest of some ridge segments is a deep canyon-like structure called a rift valley. This structure is evidence that tensional forces are actively pulling the oceanic crust apart at the ridge crest. Thingvellir National Park, Iceland, is located on the western margin of a rift valley roughly 30 kilometers wide. This rift valley is connected to a similar feature that extends along the crest of the Mid-Atlantic Ridge. The cliff in the left half of the image approximates the eastern edge of the North American plate. Smart Figure 2.12 Rift Valley in Iceland. The mechanism that operates along the oceanic ridge system to create new seafloor is appropriately called seafloor spreading. Spreading typically averages around 5 centimeters per year, roughly the same rate at which human fingernails grow. Comparatively slow spreading rates of 2 centimeters per year are found along the Mid-Atlantic Ridge, whereas spreading rates exceeding 15 centimeters per year have been measured along sections of the East Pacific Rise. Although these rates of seafloor production are slow on a human time scale, they are rapid enough to have generated all of Earth's current oceanic lithosphere within the past 200 million years. Watch Mobile Field Trip, Iceland. The primary reason for the elevated position of the oceanic ridge is that newly created oceanic lithosphere is hot and, therefore, less dense than cooler rocks located away from the ridge axis. As soon as new lithosphere forms, it is slowly yet continually displaced away from the zone of mantle upwelling. Thus, it begins to cool and contract, thereby increasing in density. This thermal contraction accounts for the increase in ocean depth away from the ridge crest. It takes about 80 million years for the temperature of oceanic lithosphere to stabilize and contraction to cease. By this time, rock that was once part of the elevated oceanic ridge system is located in the deep ocean basin, where it may be buried by substantial accumulations of sediment. In addition, as the plate moves away from the ridge, cooling of the underlying asthenosphere causes its upper layers to become increasingly rigid. Thus, oceanic lithosphere is generated by cooling of the asthenosphere from the top down. Stated another way, the thickness of oceanic lithosphere is age-dependent. The older it is, the greater its thickness. Oceanic lithosphere that exceeds 80 million years in age is about 100 kilometers thick, approximately its maximum thickness. Continental rifting. Divergent boundaries can develop within a continent and may cause the landmass to split into 2 or more smaller segments separated by an ocean basin. Continental rifting begins when plate motions produce tensional forces that pull and stretch the lithosphere. This stretching, in turn, promotes mantle upwelling and broad upwarping of the overlying lithosphere. This process thins the lithosphere and breaks the brittle crustal rocks into large blocks. As the tectonic forces continue to pull apart the crust, the broken crustal fragments sink, generating an elongated depression called a continental rift, which can widen to form a narrow sea. And eventually a new ocean basin. The formation of new oceans is discussed further in Chapter 10. Smart Figure 2.13 Continental Rifting, Formation of New Ocean Basins. Smart Figure 2.13 Full Alternative Text Description Watch Tutorial, Divergent Boundaries. An example of an active continental rift is the East African Rift. Whether this rift will eventually result in the breakup of Africa is a topic of ongoing research. Nevertheless, the East African Rift is an excellent model of the initial stage in the breakup of a continent. Here, tensional forces have stretched and thinned the lithosphere, allowing molten rock to ascend from the mantle. Evidence for this upwelling includes several large volcanic mountains, including Mount Kilimanjaro and Mount Kenya, the tallest peaks in Africa. Research suggests that if rifting continues, the Rift Valley will lengthen and deepen. At some point, the Rift Valley will become a narrow sea with an outlet to the ocean. The Red Sea, formed when the Arabian Peninsula split from Africa, is a modern example of such a feature and provides us with a view of how the Atlantic Ocean may have looked in its infancy. The East African Rift Valley represents the early stage in the breakup of a continent. Areas shown in red consist of lithosphere that has been stretched and thinned, allowing magma to well up from the mantle. Smart Figure 2.14 East African Rift Valley. Did you know? Watch Condor video, Continental Rifting. The remains of some of the earliest humans, Homo habilis and Homo erectus, were discovered by anthropologists Lewis and Mary Leakey in the East African Rift. Scientists consider this region to be the birthplace of the human race. Concept checks 2.4. 1. Sketch or describe how two plates move in relation to each other along divergent plate boundaries. 2. What is the average rate of seafloor spreading in modern oceans? 3. List 4 features that characterize the oceanic ridge system. 4. Briefly describe the process of continental rifting. Name a location where is it occurring today. 2.5 Convergent plate boundaries and subduction. Compare and contrast the 3 types of convergent plate boundaries and name a location where each type can be found. New lithosphere is constantly being produced at the oceanic ridges. However, our planet is not growing larger, its total surface area remains constant. A balance is maintained because older, denser portions of oceanic lithosphere descend into the mantle at a rate equal to seafloor production. This activity occurs along convergent plate boundaries, where two plates move toward each other and the leading edge of one is bent downward as it slides beneath the other. Convergent boundaries are also called subduction zones because they are sites where lithosphere is descending into the mantle. Subduction occurs because the density of the descending lithospheric plate is greater than the density of the underlying asthenosphere. Recall that oceanic crust has a greater density than continental crust because it is largely composed of dense ferromagnesian-rich mineral. In general, old oceanic lithosphere is about 2% more dense than the underlying asthenosphere, causing it to sink much like an anchor on a ship. Continental lithosphere, in contrast, is less dense than the underlying asthenosphere and tends to resist subduction. However, there are a few locations where continental lithosphere is thought to have been forced below an overriding plate, albeit to relatively shallow depths. Deep ocean trenches are long, linear depressions in the seafloor that are generally located only a few hundred kilometers offshore of either a continent or a chain of volcanic islands such as the Aleutian Chain. These underwater surface features are produced where oceanic lithosphere bends as it descends into the mantle along subduction zones. An example is the Peru-Chile Trench, located along the west coast of South America. It is more than 4,500 kilometers long, and its floor is as much as 8 kilometers below sea level. Western Pacific trenches, including the Mariana and Tonga trenches, are even deeper than those of the Eastern Pacific. Slabs of oceanic lithosphere descend into the mantle at angles that vary from a few degrees to nearly vertical. The angle at which oceanic lithosphere subducts depends largely on its age and, therefore, its density. For example, when seafloor spreading occurs relatively near a subduction zone, as is the case along the coast of Chile, the subducting lithosphere is young and buoyant, which results in a low angle of descent. As the two plates converge, the overriding plate scrapes over the top of the subducting plate below, a type of forced subduction. Consequently, the region around the Peru, Chile Trench experiences great earthquakes, including the 2010 Chilean earthquake, one of the 10 largest on record. As oceanic lithosphere ages, it gradually cools, which causes it to thicken and increase in density. In parts of the western Pacific, some oceanic lithosphere is 180 million years old, the thickest and densest in today's oceans. The very dense slabs in this region typically plunge into the mantle at angles approaching 90 degrees. This largely explains why most trenches in the western Pacific are deeper than trenches in the eastern Pacific. Although all convergent zones have the same basic characteristics, they may vary considerably depending on the type of crustal material involved and the tectonic setting. Convergent boundaries can form between one oceanic plate and one continental plate, between two oceanic plates, or between two continental plates. Smart Figure 2.153 Types of convergent plate boundaries. Smart Figure 2.15 Full alternative text description. Oceanic, continental convergence. When the leading edge of a plate capped with continental crust converges with a slab of oceanic lithosphere, the buoyant continental block remains floating, while the denser oceanic slab sinks into the mantle. When a descending oceanic slab reaches a depth of about 100 kilometers, melting is triggered within the wedge of hot asthenosphere that lies above it. But how does the subduction of a cool slab of oceanic lithosphere cause mantle rock to melt? The answer lies in the fact that water contained in the descending plates acts the way salt does to melt ice. That is, wet rock in a high-pressure environment melts at substantially lower temperatures than does dry rock of the same composition. Watch tutorial, Continental Boundaries. Sediments and oceanic crust contain large amounts of water, which is carried to great depths by a subducting plate. As the plate plunges downward, heat and pressure drive out water from the hydrated minerals in the subducting slab. At a depth of roughly 100 kilometers. The wedge of mantle rock is sufficiently hot that the introduction of water from the slab below leads to some melting. This process, called partial melting, is thought to generate some molten material, which is mixed with unmelted mantle rock. Being less dense than the surrounding mantle, this hot mobile material gradually rises toward the surface. Depending on the environment, these mantle-derived masses of molten rock may ascend through the crust and give rise to a volcanic eruption. However, much of this material never reaches the surface but solidifies at depth, a process that thickens the crust. The volcanoes of the towering Andes were produced by molten rock generated by the subduction of the Nazca Plate beneath the South American continent. Mountain systems like the Andes, which are produced in part by volcanic activity associated with the subduction of oceanic lithosphere, are called continental volcanic arcs. The Cascade Range in Washington, Oregon, and California is another mountain system consisting of several well-known volcanoes, including Mount Rainier, Mount Shasta, Mount St. Helens, and Mount Hood. This active volcanic arc also extends into Canada, where it includes Mount Garibaldi and Mount Silverthrone. Figure 2.16 Example of an oceanic, continental convergent plate boundary. The Cascade Range is a continental volcanic arc formed by the subduction of the Juan de Fuca Plate below the North American Plate. Mount Hood, Oregon, is one of more than a dozen large composite volcanoes in the Cascade Range. Figure 2.16 Full alternative text description. Oceanic convergence. An oceanic convergent boundary has many features in common with oceanic, continental plate margins. Where two oceanic slabs converge, one descends beneath the other, initiating volcanic activity by the same mechanism that operates at all subduction zones. Water released from the subducting slab of oceanic lithosphere triggers melting in the hot wedge of mantle rock above. In this setting, volcanoes grow up from the ocean floor rather than upon a continental platform. Sustained subduction eventually results in a chain of volcanic structures large enough to emerge as islands. The newly formed land, consisting of an arc-shaped chain of volcanic islands, is called a volcanic island arc or simply an island arc. The Aleutian Islands are a volcanic island arc produced by the subduction of the Pacific Plate beneath the North American Plate. Notice that the volcanoes of the Aleutian chain extend into Alaska proper. Figure 2.17 Volcanoes in the Aleutian chain. The Aleutian, Mariana, and Tonga Islands are examples of relatively young volcanic island arcs. Island arcs are generally located 120 to 360 kilometers from a deep ocean trench. Located adjacent to the island arcs just mentioned are the Aleutian Trench, the Mariana Trench, and the Tonga Trench. Most volcanic island arcs are located in the western Pacific. Only two are located in the Atlantic, the Lesser Antilles Arc, on the eastern margin of the Caribbean Sea, and the Sandwich Islands, located off the tip of South America. The Lesser Antilles are a product of the subduction of the Atlantic seafloor beneath the Caribbean Plate. Located within this volcanic arc are the Virgin Islands of the United States and Britain as well as Martinique, where Mount Pelee erupted in 1902, destroying the town of Saint Pierre and killing an estimated 28,000 people. This chain of islands also includes Montserrat, where volcanic activity has occurred as recently as 2010. Island arcs are typically simple structures made of numerous volcanic cones underlain by oceanic crust that is generally less than 20 kilometers thick. Some island arcs, however, are more complex and are underlain by highly deformed crust that may reach 35 kilometers in thickness. Examples include Japan, Indonesia, and the Alaskan Peninsula. These island arcs are built on material generated by earlier episodes of subduction or on small slivers of continental crust that have rafted away from the mainland. Continental convergence. The third type of convergent boundary results when one landmass moves toward the margin of another because of subduction of the intervening seafloor. Whereas oceanic lithosphere tends to be dense and readily sinks into the mantle, the buoyancy of continental material generally inhibits it from being subducted, at least to any great depth. Consequently, a collision between two converging continental fragments ensues, Figure 2. 18b. This process folds and deforms the accumulation of sediments and sedimentary rocks along the continental margins as if they had been placed in a gigantic vise. The result is the formation of a new mountain belt composed of deformed sedimentary and metamorphic rocks that often contain slivers of oceanic lithosphere. Smart Figure 2.18. The collision of India and Eurasia formed the Himalayas. The ongoing collision of the subcontinent of India with Eurasia began about 50 million years ago and produced the majestic Himalayas. It should be noted that both India and Eurasia were moving as these land masses collided. The map in Part C illustrates only the movement of India. Smart Figure 2.18. Full alternative text description. Watch animation, collision of India and Eurasia. Such a collision began about 50 million years ago, when the subcontinent of India rammed into Asia, producing the Himalayas, the most spectacular mountain range on Earth. During this collision, the continental crust buckled and fractured and was generally shortened horizontally and thickened vertically. In addition to the Himalayas, several other major mountain systems, including the Alps, Appalachians, and Urals, formed as continental fragments collided. This topic will be considered further in Chapter 11. Concept checks 2.5. 1. Explain why the rate of lithosphere production is roughly equal to the rate of lithosphere destruction. 2. Why does oceanic lithosphere subduct, while continental lithosphere does not? 3. What characteristic of a slab of oceanic lithosphere leads to the formation of a deep oceanic trench as opposed to one that is less deep? 4. What distinguishes a continental volcanic arc from a volcanic island arc? 5. Briefly describe how mountain belts such as the Himalayas form. 2.6. Transform plate boundaries. Describe the relative motion along a transform fault boundary and locate several examples of transform faults on a plate boundary map. Along a transform plate boundary, also called a transform fault, plates slide horizontally past one another without the production or destruction of lithosphere. The nature of transform faults was discovered in 1965 by Canadian geologist J. Tuzo Wilson, who proposed that these large faults connected two spreading centers or, less commonly, two trenches. Most transform faults are found on the ocean floor, where they offset segments of the oceanic ridge system, producing a step-like plate margin. Notice that the zigzag shape of the mid-Atlantic ridge in Figure 2.10 roughly reflects the shape of the original rifting that caused the breakup of the supercontinent of Pangaea. Most transform faults offset segments of a spreading center, producing a plate margin that exhibits a zigzag pattern. Smart Figure 2.19 Full alternative text description. Smart Figure 2.19 Transform plate boundaries. Watch tutorial, Transform boundaries. Typically, transform faults are part of prominent linear breaks in the seafloor known as fracture zones, which include both active transform faults and their inactive extensions into the plate interior. In a fracture zone, the active transform fault lies only between the two offset ridge segments. It is generally defined by weak, shallow earthquakes. On each side of the fault, the seafloor moves away from the corresponding ridge segment. Thus, between the ridge segments, these adjacent slabs of oceanic crust are grinding past each other along a transform fault. Beyond the ridge crests, these faults are inactive because the rock on either side moves in the same direction. However, these inactive faults are preserved as linear topographic depressions. The trend of these fracture zones roughly parallels the direction of plate motion at the time of their formation. Thus, these structures help geologists map the direction of plate motion in the geologic past. Transform faults also provide the means by which the oceanic crust created at ridge crests can be transported to a site of destruction, the deep ocean trenches. Figure 2.20 illustrates this situation. Notice that the Juan de Fuca plate moves in a southeasterly direction, eventually being subducted under the west coast of the United States and Canada. The southern end of this plate is bounded by a transform fault called the Mendocino Fault. This transform boundary connects the Juan de Fuca ridge to the Cascadia subduction zone. Therefore, it facilitates the movement of the crustal material created at the Juan de Fuca ridge to its destination beneath the North American continent. Figure 2.20 Transform faults facilitate plate motion. Seafloor generated along the Juan de Fuca ridge moves southeastward, past the Pacific plate. Eventually it subducts beneath the North American plate. Thus, this transform fault connects a spreading center to a subduction zone. Also shown is the San Andreas Fault, a transform fault connecting a spreading center located in the Gulf of California with the Mendocino Fault. Figure 2.20 Full alternative text description. Like the Mendocino Fault, most other transform fault boundaries are located within the ocean basins, however, a few cut through continental crust. Two examples are the earthquake-prone San Andreas Fault of California and New Zealand's Alpine Fault. Notice in Figure 2.20 that the San Andreas Fault connects a spreading center located in the Gulf of California to the Cascadia subduction zone and the Mendocino Fault. Along the San Andreas Fault, the Pacific Plate is moving toward the northwest, past the North American Plate. If this movement continues, the part of California west of the fault zone, including Mexico's Baja Peninsula, will become an island off the west coast of the United States and Canada. However, a more immediate concern is the earthquake activity triggered by movements along this fault system. This aerial view shows the offset in the dry channel of Wallace Creek near Taft, California. Smart Figure 2.21 Movement along the San Andreas Fault. Did you know? Watch Mobile Field Trip, the San Andreas Fault. The Great Alpine Fault is a transform fault that runs through New Zealand's South Island. The northwestern part of the South Island sits on the Australian Plate, whereas the rest of the island lies on the Pacific Plate. As with its sister fault, California's San Andreas, the rocks on one side of this fault have moved several hundred miles relative to the rocks on the other side. Concept checks 2.6. 1. Sketch or describe how two plates move in relation to each other along a transform plate boundary. 2. List two characteristics that differentiate transform faults from the two other types of plate boundaries. 2.7 How do plates and plate boundaries change? Explain why plates such as the African and Antarctic plates are increasing in size, while the Pacific plate is decreasing in size. Although Earth's total surface area does not change, the size and shape of individual plates are constantly changing. For example, the African and Antarctic plates, which are mainly bounded by divergent boundaries, sites of seafloor production, are continually growing in size as new lithosphere is added to their margins. By contrast, the Pacific plate is being consumed into the mantle along much of its flanks faster than it is being generated along the East Pacific rise and thus is diminishing in size. Another result of plate motion is that boundaries also migrate. For example, the position of the Peru-Chile Trench, which is the result of the Nazca plate being bent downward as it descends beneath the South American plate, has changed over time. Because of the westward drift of the South American plate relative to the Nazca plate, the Peru-Chile Trench has migrated in a westerly direction as well. Plate boundaries can also be created or destroyed in response to changes in the forces acting on the lithosphere. For example, some plates carrying continental crust are presently moving toward one another. In the South Pacific, Australia is moving northward, towards southern Asia. If Australia continues its northward migration, the boundary separating it from Asia will eventually disappear as these plates become one. Other plates are moving apart. Recall that the Red Sea is the site of a relatively new spreading center that came into existence less than 20 million years ago, when the Arabian Peninsula began to break apart from Africa. The breakup of Pangaea is a classic example of how plate boundaries change through geologic time. The breakup of Pangaea. Wegener used evidence from fossils, rock types, and ancient climates to create a jigsaw puzzle fit of the continents, thereby creating his supercontinent of Pangaea. By employing modern tools not available to Wegener, geologists have recreated the steps in the breakup of this supercontinent, an event that began about 180 million years ago. From this work, the dates when individual crustal fragments separated from one another and their relative motions have been well established. Figure 2.22 Full alternative text description. Figure 2.22 The breakup of Pangaea. An important consequence of Pangaea's breakup was the creation of a new ocean basin, the Atlantic. As you can see in Figure 2.22, splitting of the supercontinent did not occur simultaneously along the margins of the Atlantic. The first split developed between North America and Africa. Here, the continental crust was highly fractured, providing pathways for huge quantities of fluid lavas to reach the surface. Today, these lavas are represented by weathered igneous rocks found along the eastern seaboard of the United States, primarily buried beneath the sedimentary rocks that form the continental shelf. Radiometric dating of these solidified lavas indicates that rifting began between 200 million and 190 million years ago. This time span represents the birth date for this section of the North Atlantic. By 130 million years ago, the South Atlantic began to open near the tip of what is now South Africa. As this zone of rifting migrated northward, it gradually opened the South Atlantic. Continued breakup of the southern landmass led to the separation of Africa and Antarctica and sent India on a northward journey. By the early Cenozoic era, about 50 million years ago, Australia had separated from Antarctica, and the South Atlantic had become a full-fledged ocean. India eventually collided with Asia, an event that began about 50 million years ago and created the Himalayas and the Tibetan highlands. About the same time, the separation of Greenland from Eurasia completed the breakup of the northern landmass. During the past 20 million years or so of Earth's history, Arabia has rifted from Africa to form the Red Sea, and Baja California has separated from Mexico to form the Gulf of California. Meanwhile, the Panama Arc joined North America and South America to produce our globe's familiar modern appearance. Did you know? Researchers estimate that continents join to form supercontinents roughly every 500 million years. Since it has been about 200 million years since Pangaea broke up, we have only 300 million years to wait before the next supercontinent is completed. Plate tectonics in the future. Geologists have extrapolated present-day plate movements into the future. Figure 2.23 illustrates where Earth's landmasses may be 50 million years from now if present plate movements persist during this time span. This reconstruction is highly idealized and based on the assumption that the processes that caused the breakup of Pangaea will continue to operate. In North America we see that the Baja Peninsula and the portion of Southern California that lies west of the San Andreas Fault will have slid past the North American plate. If this northward migration continues, Los Angeles and San Francisco will pass each other in about 10 million years, and in about 60 million years the Baja Peninsula will begin to collide with the Aleutian Islands. Figure 2.23 The world as it may look 50 million years from now. If Africa maintains its northward path, it will continue to collide with Eurasia. The result will be the closing of the Mediterranean, the last remnant of a once vast ocean called the Tethys Ocean, and the initiation of another major mountain-building episode. Australia will be astride the equator and, along with New Guinea, will be on a collision course with Asia. Meanwhile, North and South America will begin to separate, while the Atlantic and Indian Oceans will continue to grow, at the expense of the Pacific Ocean. A few geologists have even speculated on the nature of the globe 250 million years in the future. In this scenario the Atlantic seafloor will eventually become old and dense enough to form subduction zones around much of its margins, not unlike the present-day Pacific Basin. Continued subduction of the Atlantic Ocean floor will result in the closing of the Atlantic Basin and the collision of the Americas with the Eurasian African landmass to form the next supercontinent, shown in Figure 2.24. Support for the possible closing of the Atlantic comes from evidence for a similar event, when an ocean predating the Atlantic closed during Pangaea's formation. Australia is also projected to collide with Southeast Asia by that time. If this scenario is accurate, the dispersal of Pangaea will end when the continents reorganize into the next supercontinent. Figure 2.24 Earth as it may appear 250 million years from now. Such projections, although interesting, must be viewed with considerable skepticism because many assumptions must be correct for these events to unfold as just described. Nevertheless, changes in the shapes and positions of continents that are equally profound will undoubtedly occur for many hundreds of millions of years to come. Only after much more of Earth's internal heat has been lost will the engine that drives plate motion cease. Did you know? When all the continents were joined to form Pangaea, the rest of Earth's surface was covered with a huge ocean called Panthalassa. Its modern descendant is the Pacific Ocean, which has been decreasing in size since the breakup of Pangaea. Concept checks 2.7. 1. Name two plates that are growing in size. Name a plate that is shrinking in size. 2. What new ocean basin was created by the breakup of Pangaea? 3. Briefly describe changes in the positions of the continents if we assume that the plate motions we see today continue 50 million years into the future. 2.8 Testing the plate tectonics model. List and explain the evidence used to support the plate tectonics theory. Some of the evidence supporting continental drift was presented earlier in this chapter. With the development of plate tectonics theory, researchers began testing this new model of how Earth works. In addition to new supporting data, new interpretations of already existing data often swayed the tide of opinion. Evidence: ocean drilling. Some of the most convincing evidence for seafloor spreading came from the deep-sea drilling project, which operated from 1966 until 1983. One of the early goals of the project was to gather samples of the ocean floor in order to establish its age. To accomplish this, the Glomar Challenger, a drilling ship capable of working in water thousands of meters deep, was built. Hundreds of holes were drilled through the layers of sediments that blanket the oceanic crust, as well as into the basaltic rocks below. Rather than use radiometric dating, which can be unreliable on oceanic rocks because of the alteration of basalt by seawater, researchers dated the seafloor by examining the fossil remains of microorganisms found in the sediments resting directly on the crust at each site. When researchers recorded the age of the sediment from each drill site and its distance from the ridge crest, they found that the sediments increased in age with increasing distance from the ridge. This finding supported the seafloor spreading hypothesis, which predicted that the youngest oceanic crust would be found at the ridge crest, the site of seafloor production, and the oldest oceanic crust would be located adjacent to the continents. The distribution and thickness of ocean floor sediments provided additional verification of seafloor spreading. Drill cores from the Glomar Challenger revealed that sediments are almost entirely absent on the ridge crest and that sediment thickness increases with increasing distance from the ridge. This pattern of sediment distribution should be expected if the seafloor spreading hypothesis is correct. Figure 2.25 Deep Sea Drilling. A. Data collected through deep-sea drilling have shown that the ocean floor is indeed youngest at the ridge axis. B. The Japanese deep-sea drilling ship Chikyu became operational in 2007. Figure 2.25 Full alternative text description. The data collected by the deep-sea drilling project also reinforced the idea that the ocean basins are geologically young because no seafloor older than 180 million years was found. By comparison, most continental crust exceeds several hundred million years in age, and some samples are more than 4 billion years old. In 1983, a new ocean drilling program was launched by the Joint Oceanographic Institutions for deep earth sampling. Now the International Ocean Discovery Program, this ongoing international effort uses multiple vessels for exploration, including the massive 210-meter-long Chikyu, which began operations in 2007. One of the goals of the IODP is to recover a complete section of the oceanic crust, from top to bottom. Evidence, mantle plumes and hot spots. Mapping volcanic islands and seamounts in the Pacific Ocean revealed several linear chains of volcanic structures. One of the most studied chains consists of at least 129 volcanoes that extend from the Hawaiian Islands to Midway Island and continue northwestward toward the Aleutian Trench. Radiometric dating of this linear structure, called the Hawaiian Island, Emperor Seamount Chain, showed that the volcanoes increase in age with increasing distance from the Big Island of Hawaii. The youngest volcanic island in the chain rose from the ocean floor less than 1 million years ago, whereas Midway Island is 27 million years old, and Detroit Seamount, near the Aleutian Trench, is about 80 million years old. Radiometric dating of the Hawaiian Islands shows that volcanic activity increases in age moving away from the Big Island of Hawaii. Figure 2.26 Hotspot volcanism and the formation of the Hawaiian chain. Figure 2.26 Full alternative text description. Did you know? Olympus Mons is a huge volcano on Mars that strongly resembles the Hawaiian volcanoes. Rising 25 kilometers above the surrounding plains, Olympus Mons owes its massive size to the lack of plate tectonics on Mars. Instead of being carried away from the hot spot by plate motion, like the Hawaiian volcanoes, Olympus Mons remained fixed and grew to a gigantic size. One widely accepted hypothesis proposes that a roughly cylindrically shaped upwelling of hot rock, called a mantle plume, is located beneath the island of Hawaii. As the hot, rocky plume ascends through the mantle, the confining pressure drops, which triggers partial melting. The surface manifestation of this activity is a hot spot, an area of volcanism, high heat flow, and crustal uplifting that is a few hundred kilometers across. As the Pacific Plate moved over a hot spot, a chain of volcanic structures known as a hotspot track was built. As shown in Figure 2.26, the age of each volcano indicates how much time has elapsed since it was situated over the mantle plume. Of approximately 40 hot spots that are thought to have formed because of upwelling of hot mantle plumes, most, but not all, have hotspot tracks. Recall from section 1.3 that a hypothesis is a tentative scientific explanation for a given set of observations. Although widely accepted, the validity of the plume hypothesis, unlike the theory of plate tectonics, remains unresolved. A closer look at the 5 largest Hawaiian islands reveals a similar pattern of ages, from the volcanically active island of Hawaii to the inactive volcanoes that make up the oldest island, Kauai. 5 million years ago, when Kauai was positioned over the hot spot, it was the only modern Hawaiian island in existence. Kauai's age is evident in the island's extinct volcanoes, which have been eroded into jagged peaks and vast canyons. By contrast, the relatively young island of Hawaii exhibits many fresh lava flows, and one of its 5 major volcanoes, Kilauea, remains active today. Evidence: paleomagnetism. You are probably familiar with how a compass operates and know that Earth's magnetic field has north and south magnetic poles. Today these magnetic poles roughly align with the geographic poles that are located where Earth's rotational axis intersects the surface. Earth's magnetic field is somewhat similar to that produced by a simple bar magnet. Invisible lines of force pass through the planet and extend from one magnetic pole to the other. A compass needle, itself a small magnet free to rotate on an axis, becomes aligned with the magnetic lines of force and points to the magnetic poles. Earth's magnetic field consists of lines of force much like those a giant bar magnet would produce if placed at the center of Earth. Figure 2.27 Earth's magnetic field. Earth's magnetic field is less obvious to us than the pull of gravity because we cannot feel it. Movement of a compass needle, however, confirms its presence. In addition, some naturally occurring minerals are magnetic and are influenced by Earth's magnetic field. One of the most common is the iron-rich mineral magnetite, which is abundant in lava flows of basaltic composition. Basaltic lavas erupt at the surface at temperatures greater than 1000 degrees Celsius, exceeding a threshold temperature for magnetism known as the Curie point. The magnetite grains in molten lava are non-magnetic, but as the lava cools, these iron-rich grains become magnetized and align themselves in the direction of the existing magnetic lines of force. Once the minerals solidify, the magnetism they possess usually remains frozen in this position. Thus, they act like a compass needle because they point toward the position of the magnetic poles at the time of their formation. Rocks that formed thousands or millions of years ago and contain a record of the direction of the magnetic poles at the time of their formation are said to possess paleomagnetism or fossil magnetism. Some sediments and sedimentary rocks also contain enough iron-bearing mineral grains to acquire a measurable amount of magnetization. Apparent polar wandering. A study of paleomagnetism in ancient lava flows throughout Europe led to an interesting discovery. Taken at face value, the magnetic alignment of iron-rich minerals in lava flows of different ages would indicate that the position of the paleomagnetic poles had changed through time. A plot of the location of the magnetic North Pole, as measured from Europe, seemed to indicate that during the past 500 million years, the pole had gradually wandered from a location near Hawaii northeastward to its present location over the Arctic Ocean. This was strong evidence that either the magnetic North Pole had migrated, an idea known as polar wandering, or that the poles had remained in place and the continents had drifted beneath them. In other words, Europe had drifted relative to the magnetic North Pole. Scientists believe that the more westerly path determined from North American data was caused by the westward drift of North America by about 24 degrees from Eurasia. The positions of the wandering paths when the land masses are reassembled in their pre-drift locations. Figure 2.28 Apparent polar wandering path. Figure 2.28 Full alternative text description. Although the magnetic poles are known to move in a somewhat erratic path, studies of paleomagnetism from numerous locations show that the positions of the magnetic poles, averaged over thousands of years, correspond closely to the positions of the geographic poles. Therefore, a more acceptable explanation for the apparent polar wandering was provided by Wegener's hypothesis. If the magnetic poles remain stationary, their apparent movement is produced by the drift of the seemingly fixed continents. Further evidence for continental drift came a few years later, when a polar wandering path was constructed for North America. For the first 300 million years or so, the paths for North America and Europe were found to be similar in direction, but separated by about 5,000 kilometers. Then, during the middle of the Mesozoic era, they began to converge on the present North Pole. The explanation for these curves is that North America and Europe were joined until the Mesozoic, when the Atlantic began to open. From this time forward, these continents continuously moved apart. When North America and Europe are moved back to their pre-drift positions, as shown in Figure 2.28b, these paths of apparent polar wandering coincide. This is evidence that North America and Europe were once joined and moved relative to the poles as part of the same continent. Magnetic reversals and seafloor spreading. More evidence emerged when geophysicists learned that over periods of hundreds of thousands of years, Earth's magnetic field periodically reverses polarity. During a magnetic reversal, the magnetic North Pole becomes the magnetic South Pole and vice versa. Lava that solidified during a period of reverse polarity is magnetized with the polarity opposite that of volcanic rocks being formed today. When rocks exhibit the same magnetism as the present magnetic field, they are said to possess normal polarity, whereas rocks exhibiting the opposite magnetism are said to have reverse polarity. Once the concept of magnetic reversals was confirmed, researchers set out to establish a time scale for these occurrences. The task was to measure the magnetic polarity of hundreds of lava flows and use radiometric dating techniques to establish the age of each flow. Figure 2.29 shows the magnetic time scale established using this technique for the past few million years. The major divisions of the magnetic time scale, crons, last for roughly 1 million years each. As more measurements became available, researchers realized that several short-lived reversals often occurred during a single chron. A. Time scale of Earth's magnetic reversals for the past 4 million years. B. This time scale was developed by establishing the magnetic polarity for lava flows of known age. Smart Figure 2.29 Time scale of magnetic reversals. Smart Figure 2.29 Full alternative text description. Meanwhile, oceanographers had begun magnetic surveys of the ocean floor in conjunction with their efforts to construct detailed maps of seafloor topography. These magnetic surveys were accomplished by towing very sensitive instruments, called magnetometers, behind research vessels. The goal of these geophysical surveys was to map variations in the strength of Earth's magnetic field that arise from differences in the magnetic properties of the underlying crustal rocks. Watch tutorial, Magnetic Reversals. Figure 2.30 Ocean floor as a magnetic recorder. A. Magnetic intensities are recorded when a magnetometer is towed across a segment of the oceanic floor. B. Notice the symmetrical stripes of low and high-intensity magnetism that parallel the axis of the Juan de Fuca ridge. The colored stripes of high-intensity magnetism occur where normally magnetized oceanic rocks enhance the existing magnetic field. Conversely, the white low-intensity stripes are regions where the crust is polarized in the reverse direction, which weakens the existing magnetic field. Figure 2.30 Full alternative text description. The first comprehensive study of this type was performed off the Pacific coast of North America and had an unexpected outcome. Researchers discovered alternating stripes of high and low-intensity magnetism, as shown in Figure 2.30b. This relatively simple pattern of magnetic variation defied explanation until 1963, when Fred Vine and D. H. Matthews demonstrated that the high and low-intensity stripe supported the concept of seafloor spreading. Vine and Matthews suggested that the stripes of high-intensity magnetism are regions where the paleomagnetism of the oceanic crust exhibits normal polarity. Consequently, these rocks enhance Earth's magnetic field. Conversely, the low-intensity stripes are regions where the oceanic crust is polarized in the reverse direction and therefore weaken the existing magnetic field. But how do parallel stripes of normally and reversely magnetized rock become distributed across the ocean floor? Vine and Matthews reasoned that as magma solidifies at the crest of an oceanic ridge, it is magnetized with the polarity of Earth's magnetic field at that time. Because of seafloor spreading, this strip of magnetized crust would gradually increase in width. When Earth's magnetic field reverses polarity, any newly formed seafloor having the opposite polarity would form in the middle of the old strip. Gradually, the two halves of the old strip would be carried in opposite directions, away from the ridge crest. Subsequent reversals would build a pattern of normal and reverse magnetic stripes, as shown in Figure 2.31. Because new rock is added in equal amounts to both trailing edges of the spreading ocean floor, we should expect the pattern of stripes found on one side of an oceanic ridge to be a mirror image of those on the other side. In fact, a survey across the mid-Atlantic ridge just south of Iceland reveals a pattern of magnetic stripes exhibiting a remarkable degree of symmetry in relation to the ridge axis. When new basaltic rocks form at mid-ocean ridges, they magnetize according to Earth's existing magnetic field. Hence, oceanic crust provides a permanent record of each reversal of our planet's magnetic field over the past 200 million years. Smart Figure 2.31 Full alternative text description. Smart Figure 2.31 Magnetic reversals and seafloor spreading. Watch animation, magnetic reversals. Concept checks 2.8. 1. What is the age of the oldest sediments recovered using deep ocean drilling? How do the ages of these sediments compare to the ages of the oldest continental rocks? 2. How do sedimentary cores from the ocean floor support the concept of seafloor spreading? 3. Assuming that hot spots remain fixed, in what direction was the Pacific Plate moving while the Hawaiian Islands were forming? 4. Describe how Fred Vine and D. H. Matthews related the seafloor spreading hypothesis to magnetic reversals. 2.9 How is plate motion measured? Describe two methods researchers use to measure relative plate motion. A number of methods are used to establish the direction and rate of plate motion. Some of these techniques not only confirm that lithospheric plates move but allow us to trace those movements back in geologic time. Geologic measurement of plate motion. Using ocean drilling ships, researchers have obtained dates for hundreds of locations on the ocean floor. By knowing the age of a rock sample and its distance from the ridge axis where it was generated, an average rate of plate motion can be calculated. Scientists use these data, combined with their knowledge of paleomagnetism stored in hardened lavas on the ocean floor and seafloor topography, to create maps that show the age of the ocean floor. The reddish-orange bands shown in Figure 2.32 range in age from the present to about 30 million years ago. The width of the bands indicates how much crust formed during that time period. For example, the reddish-orange band along the East Pacific Rise is more than 3 times wider than the same color band along the Mid-Atlantic Ridge. Therefore, the rate of seafloor spreading has been approximately 3 times faster in the Pacific Basin than in the Atlantic. Figure 2.32 Age of the ocean floor. Maps of this type also provide clues to the current direction of plate movement. Notice the offsets in the ridges. These are transform faults that connect the spreading centers. Recall that transform faults are aligned parallel to the direction of spreading. Careful measurement of transform faults reveals the direction of plate movement. To establish the direction of plate motion in the past, geologists can examine the long fracture zones that extend for hundreds or even thousands of kilometers from ridge crests. Fracture zones are inactive extensions of transform faults and are therefore a record of past directions of plate motion. Unfortunately, most of the ocean floor is less than 180 million years old, so to look deeper into the past, researchers must rely on paleomagnetic evidence provided by continental rocks. Measuring plate motion from space. You are likely familiar with the global positioning system used to locate one's position in order to provide directions to some other location. The GPS employs satellites that send radio signals that are intercepted by GPS receivers located at Earth's surface. The exact position of a site is determined by simultaneously establishing the distance from the receiver to 4 or more satellites. Researchers use specially designed equipment to locate a point on Earth to within a few millimeters. To establish plate motions, GPS data are collected at numerous sites repeatedly over a number of years. Data obtained from GPS and other techniques are shown in Figure 2.33. Calculations show that Hawaii is moving in a northwesterly direction toward Japan at 8.3 centimeters per year. A location in Maryland is retreating from a location in England at a speed of 1.7 centimeters per year, a value close to the 2.0 centimeters per year spreading rate established from paleomagnetic evidence obtained for the North Atlantic. Techniques involving GPS devices have also been useful in confirming small-scale crustal movements, like those occurring along faults in regions known to be tectonically active. The red arrows show plate motion at selected locations, based on GPS data. Longer arrows represent faster spreading rates. The small black arrows and labels show seafloor spreading velocities based mainly on paleomagnetic data. Figure 2.33 Rates of plate motion. Figure 2.33 Full alternative text description. Concept checks 2.9. 1. What do transform faults that connect spreading centers indicate about plate motion? 2. Refer to Figure 2.33 to determine which 3 plates appear to exhibit the highest rates of motion. 2.10 What drives plate motions? Describe plate, mantle convection and explain 2 of the primary driving forces of plate motion. Researchers are in general agreement that some type of convection, with hot mantle rocks rising and cold, dense oceanic lithosphere sinking, is the ultimate driver of plate tectonics. Many of the details of this convective flow, however, remain topics of debate in the scientific community. Forces that drive plate motion. Geophysical evidence confirms that although the mantle consists almost entirely of solid rock, it is hot and weak enough to exhibit a slow, fluid-like convective flow. The simplest type of convection is analogous to heating a pot of water on a stove. Heating the base of a pot warms the water, making it less dense and causing it to rise in relatively thin sheets or blobs that spread out at the surface. As the surface layer cools, its density increases, and the cooler water sinks back to the bottom of the pot, where it is reheated until it achieves enough buoyancy to rise again. Mantle convection is similar to, but considerably more complex than, the model just described. As a stove warms the water in the bottom of a cooking pot, the heated water expands, becomes less dense, and rises. Simultaneously, the cooler, denser water near the top sinks. Figure 2.34 Convection in a cooking pot. Geologists generally agree that subduction of cold, dense slabs of oceanic lithosphere is a major driving force of plate motion. This phenomenon, called slab pull, occurs because cold slabs of oceanic lithosphere are more dense than the underlying warm asthenosphere and hence, sink like a rock, meaning that they are pulled down into the mantle by gravity. Figure 2.35 Full alternative text description. Another important driving force is ridge push. This gravity-driven mechanism results from the elevated position of the oceanic ridge, which causes slabs of lithosphere to slide down the flanks of the ridge. Despite its importance, ridge push contributes far less to plate motions than slab pull. The primary evidence for this is that the fastest-moving plates, the Pacific, Nazca, and Cocos plates, have extensive subduction zones along their margins. By contrast, the spreading rate in the North Atlantic Basin, which is nearly devoid of subduction zones, is one of the lowest, at about 2.5 centimeters per year. Figure 2.35 Forces that act on lithospheric plates. Did you know? Because tectonic processes are powered by heat from Earth's interior, the forces that drive plate motion will cease sometime in the distant future. The work of external forces, however, will continue to erode Earth's surface. Eventually, land masses will be nearly flat. What a different world it will be, an Earth with no earthquakes, no volcanoes, and no mountains. Models of plate, mantle convection. Although convection in the mantle has yet to be fully understood, researchers generally agree on the following. Convective flow, in which warm, buoyant mantle rocks rise while cool, dense lithospheric plates sink, is the underlying driving force for plate movement. Mantle convection and plate tectonics are part of the same system. Subducting oceanic plates drive the cold downward-moving portion of convective flow, while shallow upwelling of hot rock along the oceanic ridge and buoyant mantle plumes are the upward-flowing arms of the convective mechanism. Convective flow in the mantle is a major mechanism for transporting heat away from Earth's interior to the surface, where it is eventually radiated into space. What is not known with certainty is the exact structure of this convective flow. Several models have been proposed for plate, mantle convection, and we will look at two of them. Whole mantle convection. One group of researchers favor some type of whole mantle convection model, also called the plume model, in which cold oceanic lithosphere sinks to great depths and stirs the entire mantle. The whole mantle model suggests that the ultimate burial ground for these subducting lithospheric slabs is the core, mantle boundary. The downward flow of these subducting slabs is balanced by buoyantly rising mantle plumes that transport hot mantle rock toward the surface. Figure 2.36 Models of mantle convection. Figure 2.36 Full alternative text description. Two kinds of plumes have been proposed, narrow tube-like plumes and giant upwellings, often referred to as megaplumes. The long, narrow plumes are thought to originate from the core, mantle boundary and produce hotspot volcanism of the type associated with the Hawaiian Islands, Iceland, and Yellowstone. Scientists believe that areas of large megaplumes, as shown in Figure 2.36a, occur beneath the Pacific Basin and southern Africa. These megaplumes are thought to explain why southern Africa has an elevation much higher than would be predicted for a stable continental landmass. In the whole mantle convection model, heat for both the narrow plumes and the megaplumes is thought to arise mainly from Earth's core, while the deep mantle provides a source for chemically distinct magmas. However, some researchers have questioned that idea and instead proposed that the source of magma for most hotspot volcanism is found in the upper mantle. Layer cake model. Some researchers argue that the mantle resembles a layer cake divided at a depth of perhaps 660 kilometers but no deeper than 1,000 kilometers. As shown in Figure 2.36b, this layered model has two zones of convection, a thin, dynamic layer in the upper mantle and a thick, larger, sluggish one located below. As with the whole mantle model, the downward convective flow is driven by the subduction of cold, dense oceanic lithosphere. However, rather than reach the lower mantle, these subducting slabs penetrate to depths of no more than 1,000 kilometers. Notice in Figure 2.36b that the upper layer in the layer cake model is littered with recycled oceanic lithosphere of various ages. Melting of these fragments is thought to be the source of magma for some of the volcanism that occurs away from plate boundaries, such as the hotspot volcanism of Hawaii. In contrast to the active upper mantle, the lower mantle is sluggish and does not provide material to support volcanism at the surface. Very slow convection within this layer likely carries heat upward, but very little mixing occurs between these two layers. Geologists continue to debate the nature of the convective flow in the mantle. As they investigate the possibilities, perhaps a widely accepted hypothesis that combines features from the layer cake model and the whole mantle convection model will emerge. Concept checks 2.10. 1. Define slab pull and ridge push. Which of these forces contributes more to plate motion? 2. Briefly describe the two models of plate, mantle convection. 3. What geologic processes are associated with the upward and downward circulation in the mantle? Concepts in review. Plate tectonics: a scientific revolution unfolds. 2.1 From continental drift to plate tectonics. Summarize the view that most geologists held prior to the 1960s regarding the geographic positions of the ocean basins and continents. 50 years ago, most geologists thought that ocean basins were very old and that continents were fixed in place. Those ideas were discarded with a scientific revolution that revitalized geology, the theory of plate tectonics. Supported by multiple kinds of evidence, plate tectonics is the foundation of modern Earth science. 2.2 Continental drift, an idea before its time. List and explain the evidence Wegener presented to support his continental drift hypothesis. Key terms: continental drift, supercontinent Pangaea. German meteorologist Alfred Wegener formulated the continental drift hypothesis in 1912. He suggested that Earth's continents are not fixed in place but move slowly over geologic time. Wegener proposed a supercontinent called Pangaea that existed about 200 million years ago, during the late Paleozoic and early Mesozoic eras. Wegener's evidence that Pangaea existed and later broke into pieces that drifted apart included the shapes of the continents, continental fossil organisms that matched across oceans, matching rock types and modern mountain belts, and sedimentary rocks that recorded ancient climates, including glaciers on the southern portion of Pangaea. Wegener's hypothesis suffered from two flaws. It proposed tidal forces as the mechanism for the motion of continents, and it implied that the continents would have plowed their way through weaker oceanic crust, like boats cutting through a thin layer of sea ice. Most geologists rejected the idea of continental drift and Wegener proposed it, and it wasn't resurrected for another 50 years. Why did Wegener choose organisms such as Glossopteris and Mesosaurus as evidence for continental drift, as opposed to other fossil organisms such as sharks or jellyfish? 2.3 The theory of plate tectonics. List the major differences between Earth's lithosphere and asthenosphere and explain the importance of each in the plate tectonics theory. Key terms: theory of plate tectonics, lithosphere, asthenosphere. Lithospheric plate. Research conducted after World War II led to new insights that helped revive Wegener's hypothesis of continental drift. Exploration of the seafloor uncovered previously unknown features, including an extremely long mid-ocean ridge system. Sampling of the oceanic crust revealed that it was quite young relative to the continents. The lithosphere, Earth's outermost rocky layer, is relatively stiff and deforms by bending or breaking. The lithosphere consists both of crust and underlying upper mantle. Beneath the lithosphere is the asthenosphere, a relatively weak layer that deforms by flowing. The lithosphere consists of about 24 segments of irregular size and shape. There are 7 large lithospheric plates, another 7 intermediate-size plates, and numerous relatively small microplates. Plates meet along boundaries that may be divergent, convergent, or transform. 2.4 Divergent plate boundaries and seafloor spreading. Sketch and describe the movement along a divergent plate boundary that results in the formation of new oceanic lithosphere. Key terms: divergent plate boundary, oceanic ridge system, rift valley, seafloor spreading, continental rift. Seafloor spreading leads to the formation of new oceanic lithosphere at mid-ocean ridge systems. As two plates move apart from one another, tensional forces open cracks in the plates, allowing magma to well up and generate new slivers of seafloor. This process generates new oceanic lithosphere at a rate of 2 to 15 centimeters each year. As it ages, oceanic lithosphere cools and becomes denser. It therefore subsides as it is transported away from the mid-ocean ridge. At the same time, the underlying asthenosphere cools, adding new material to the underside of the plate, which consequently thickens. Divergent boundaries are not limited to the seafloor. Continents can break apart, too, starting with a continental rift and potentially producing a new ocean basin between the two sides of the rift. 2.5 Convergent plate boundaries and subduction. Compare and contrast the three types of convergent plate boundaries and name a location where each type can be found. Key terms. Convergent plate boundary: deep ocean trench, partial melting continental volcanic arc, volcanic island arc. When plates move toward one another, oceanic lithosphere is subducted into the mantle, where it is recycled. Subduction manifests itself on the ocean floor as a deep linear trench. The subducting slab of oceanic lithosphere can descend at a variety of angles, from nearly horizontal to nearly vertical. Aided by the presence of water, the subducted oceanic lithosphere triggers melting in the mantle, which produces magma. The magma is less dense than the surrounding rock and will rise. It may cool at depth, thickening the crust, or it may make it all the way to Earth's surface, where it erupts as a volcano. A line of volcanoes that emerge through continental crust is termed a continental volcanic arc, while a line of volcanoes that emerge through an overriding plate of oceanic lithosphere is a volcanic island arc. Continental crust resists subduction due to its relatively low density, and so when an intervening ocean basin is completely destroyed through subduction, the continents on either side collide, generating a new mountain range. Sketch a typical continental volcanic arc and label the key parts. Then repeat the drawing with an overriding plate made of oceanic lithosphere. 2.6 Transform plate boundaries. Describe the relative motion along a transform fault boundary and locate several examples of transform faults on a plate boundary map. Key terms. Transform plate boundary: fracture zone. At a transform boundary, lithospheric plates slide horizontally past one another. No new lithosphere is generated, and no old lithosphere is consumed. Shallow earthquakes signal the movement of these slabs of rock as they grind past their neighbors. The San Andreas Fault in California is an example of a transform boundary in continental crust, while the fracture zones between segments of the Mid-Atlantic Ridge are transform faults in oceanic crust. On the accompanying tectonic map of the Caribbean, find the Enriquillo Fault. What kind of plate boundary is shown here? Are there any other faults in the area that show the same type of motion? Figure 2.12-1 Full alternative text description. 2.7 How do plates and plate boundaries change? Explain why plates such as the African and Antarctic plates are increasing in size, while the Pacific plate is decreasing in size. Although the total surface area of Earth does not change, the shapes and sizes of individual plates are constantly changing as a result of subduction and seafloor spreading. Plate boundaries can also be created or destroyed in response to changes in the forces acting on the lithosphere. The breakup of Pangaea and the collision of India with Eurasia are two examples of how plates change through geologic time. 2.8 Testing the plate tectonics model. List and explain the evidence used to support the plate tectonics theory. Key terms. Mantle plume hotspot track Curie point. Paleomagnetism magnetic reversal normal polarity reverse polarity magnetic time scale magnetometer. Multiple lines of evidence have verified the plate tectonics model. For instance, the deep-sea drilling project found that the age of the seafloor increases with distance from a mid-ocean ridge. The thickness of sediment atop this seafloor is also proportional to distance from the ridge. Older lithosphere has had more time to accumulate sediment. A hot spot is an area of volcanic activity where a mantle plume reaches Earth's surface. Volcanic rocks generated by hotspot volcanism provide evidence of both the direction and rate of plate movement over time. Magnetic minerals such as magnetite align themselves with Earth's magnetic field as rock forms. These fossil magnets are records of the ancient orientation of Earth's magnetic field. This is useful to geologists in two ways. It allows a given stack of rock layers to be interpreted in terms of their orientation relative to the magnetic poles through time, and reversals in the orientation of the magnetic field are preserved as stripes of normal and reversed polarity in the oceanic crust. Magnetometers reveal this signature of seafloor spreading as a symmetrical pattern of magnetic stripes parallel to the axis of the mid-ocean ridge. 2.9 How is plate motion measured? Describe two methods researchers use to measure relative plate motion. Data collected from the ocean floor has established the direction and rate of motion of lithospheric plates. Transform faults point in the direction the plate is moving. Establishing dates for seafloor rocks helps to calibrate the rate of motion. GPS satellites can be used to accurately measure the motion of special receivers to within a few millimeters. These real-time data support the inferences made from seafloor observations. On average, plates move at about the same rate human fingernails grow, about 5 centimeters per year. 2.10 What drives plate motions? Describe plate, mantle convection and explain two of the primary driving forces of plate motion. Key terms: convection, slab pull, ridge push. Some kind of convection appears to drive the motion of plates. Slabs of oceanic lithosphere sink at subduction zones because the subducted slab is denser than the underlying asthenosphere. In this process, called slab pull, Earth's gravity tugs at the slab, drawing the rest of the plate toward the subduction zone. As oceanic lithosphere slides down the mid-ocean ridge, it exerts a small additional force, called ridge push. Convection may occur throughout the entire mantle, as suggested by the whole mantle model. Or it may occur in two layers within the mantle, the active upper mantle and the sluggish lower mantle, as proposed in the layer cake model. Compare and contrast mantle convection with the operation of a lava lamp. Give it some thought. 1. Refer to section 1.3, titled The Nature of Scientific Inquiry, to answer the following. A. What observations led Alfred Wegener to develop his continental drift hypothesis? B. Why did most of the scientific community reject the continental drift hypothesis? C. Do you think Wegener followed the basic principles of scientific inquiry? Support your answer. 2. Refer to the accompanying diagrams illustrating the three types of convergent plate boundaries and complete the following. A. Identify each type of convergent boundary. B. On what type of crust do volcanic island arcs develop? C. Why are volcanoes largely absent where two continental blocks collide? D. Describe two ways that oceanic convergent boundaries are different from oceanic, continental boundaries. How are they similar? Figure 2.12-1 Full alternative text description. 3. Some people predict that California will sink into the ocean. Is this idea consistent with the theory of plate tectonics? Explain. 4. Volcanic islands that form over mantle plumes, such as the Hawaiian chain, are home to some of Earth's largest volcanoes. However, several volcanoes on Mars are gigantic compared to any on Earth. What does this difference tell us about the role of plate motion in shaping the Martian surface? 5. Refer to the accompanying hypothetical plate map to answer the following questions. A. How many portions of plates are shown? B. Explain why active volcanoes are more likely to be found on continents A and B than on continent C. C. Provide one scenario in which volcanic activity might be triggered on continent C. Figure 2.12-1 Full alternative text description. 6. Australian marsupials have direct fossil links to marsupial possums found in the Americas. Yet the modern marsupials in Australia are markedly different from their American relatives. How does the breakup of Pangea help to explain these differences? 7. Density is a key component in the behavior of Earth materials and is essential to understanding important aspects of the plate tectonics model. Describe 3 different ways that density and/or density differences play a role in plate tectonics. 8. Explain how the processes that create hotspot volcanic chains differ from the processes that generate volcanic island arcs. 9. Imagine that you are studying seafloor spreading along 2 different oceanic ridges. Using data from a magnetometer, you produced the 2 accompanying maps. From these maps, what can you determine about the relative rates of seafloor spreading along these 2 ridges? Explain. Figure 2.12-1 Full alternative text description. 10. Refer to the accompanying plate motion map and these pairs of cities to complete the following. A. B. Which pair of cities is moving apart as a result of plate motion? C. Which pair of cities is moving closer as a result of plate motion? D. Which pair of cities is not presently moving relative to each other? Figure 2.12-1 Full alternative text description. Mastering Geology trademark. Looking for additional review and test prep materials? Visit the study area in Mastering Geology to enhance your understanding of this chapter's content by accessing a variety of resources, including self-study quizzes, geoscience animations, smart figures, mobile field trips, Project Condor quadcopter videos, in the news RSS feeds, flashcards, web links, and an optional Pearson e-text. Chapter 3 Matter and Minerals. The Cave of Crystals, Chihuahua, Mexico, contains giant gypsum crystals, some of the largest natural crystals ever found. Focus on concepts. Each statement represents the primary learning objective for the corresponding major heading within the chapter. After you complete the chapter, you should be able to 3.1 List the main characteristics that an earth material must possess to be considered a mineral and describe each characteristic. 3.2 Compare and contrast the 3 primary particles contained in atoms. 3.3 Distinguish among ionic bonds, covalent bonds, and metallic bonds. 3.4 List and describe the properties used in mineral identification. 3.5 Explain how minerals are classified and name the most abundant mineral group in Earth's crust. 3.6 Sketch the silicon, oxygen tetrahedron and explain how this fundamental building block joins together to form various silicate structures. 3.7 Compare and contrast the light silicates with the dark silicates and list 3 common minerals in each group. 3.8 List the common non-silicate minerals and explain why each is important. 3.9 Discuss Earth's mineral resources in terms of renewability. Differentiate between mineral resources and/or deposits. Earth's crust and oceans are home to a wide variety of useful and essential minerals. Most people are familiar with the common uses of many basic metals, including aluminum in beverage cans, copper in electrical wiring, and gold and silver in jewelry. But some people are not aware that pencil, lead, contains the greasy-feeling mineral graphite and that bath powders and many cosmetics contain the mineral talc. Moreover, many do not know that dentists use drill bits impregnated with diamonds to drill through tooth enamel. In fact, practically every manufactured product contains materials obtained from minerals. In addition to the economic uses of rocks and minerals, every geologic process in some way depends on the properties of these basic earth materials. Events such as volcanic eruptions, mountain building, weathering and erosion, and even earthquakes involve rocks and minerals. Consequently, a basic knowledge of earth materials is essential to understanding all geologic phenomena. 3.1 Minerals, building blocks of rocks. List the main characteristics that an earth material must possess to be considered a mineral and describe each characteristic. We begin our discussion of earth materials with an overview of mineralogy. Because minerals are the building blocks of rocks. Humans have used minerals for both practical and decorative purposes for thousands of years. For example, the common mineral quartz is the source of silicon for computer chips. The first earth materials mined were flint and chert, which humans fashioned into weapons and cutting tools. As early as 3700, Egyptians began mining gold, silver, and copper. By 2200, humans had discovered how to combine copper with tin to make bronze, a strong, hard alloy. Later, a process was developed to extract iron from minerals such as hematite, a discovery that marked the decline of the Bronze Age. During the Middle Ages, mining of a variety of minerals became common, and the impetus for the formal study of minerals was in place. The term mineral is used in several different ways. For example, those concerned with health and fitness extol the benefits of vitamins and minerals. The mining industry typically uses the word mineral to refer to anything extracted from earth, such as coal, iron ore, or sand and gravel. The guessing game 20 questions usually begins with the question: is it animal, vegetable, or mineral? What criteria do geologists use to determine whether something is a mineral? A collection of well-developed quartz crystals found near Hot Springs, Arkansas. Figure 3.1 Quartz crystals. Defining a mineral. Geologists define mineral as any naturally occurring inorganic solid that possesses an orderly crystalline structure and a definite chemical composition that allows for some variation. Thus, earth materials that are classified as minerals exhibit the following characteristics. 1. Naturally occurring. Minerals form by natural geologic processes. Synthetic materials, meaning those produced in a laboratory or by human intervention, are not considered minerals. 2. Generally inorganic. Inorganic crystalline solids, such as ordinary table salt, that are found naturally in the ground are considered minerals. Many marine animals secrete inorganic compounds, such as calcium carbonate, in the form of shells and coral reefs. If these materials are buried and become part of the rock record, geologists consider them minerals. 3. Solid substance. Only solid crystalline substances are considered minerals. Ice fits this criterion and is considered a mineral, whereas liquid water and water vapor do not. 4. Orderly crystalline structure. Minerals are crystalline substances, made up of atoms that are arranged in an orderly, repetitive manner. This orderly packing of atoms is reflected in regularly shaped objects called crystals. Some naturally occurring solids, such as volcanic glass, lack a repetitive atomic structure and are not considered minerals. 5. Definite chemical composition that allows for some variation. Most minerals are chemical compounds having compositions that can be expressed by a chemical formula. For example, the common mineral quartz has the formula SiO2, which indicates that quartz consists of silicon and oxygen atoms, in a 1:2 ratio. This proportion of silicon to oxygen is true for any sample of pure quartz, regardless of its origin. However, the compositions of some minerals can vary within specific, well-defined limits. This occurs because certain elements can substitute for others of similar size without changing the mineral's internal structure. The arrangement of atoms into basic building blocks that have a cubic shape results in regularly shaped cubic crystals. Figure 3.2 Arrangement of sodium and chloride ions in the mineral halite. Figure 3.2 Full alternative text description. What is a rock? In contrast to minerals, rocks are more loosely defined. Simply, a rock is any solid mass of mineral, or mineral-like, matter that occurs naturally as part of our planet. Most rocks, like the sample of granite shown in Figure 3.3, occur as aggregates of several different minerals. The term aggregate implies that the minerals are joined in such a way that their individual properties are retained. Note that the different minerals that make up granite can be easily identified. However, some rocks are composed almost entirely of one mineral. A common example is the sedimentary rock limestone, which is an impure mass of the mineral calcite. Shown here is a hand sample of the igneous rock granite and 3 of its major constituent minerals. Smart Figure 3.3 Most rocks are aggregates of minerals. Did you know? Archaeologists discovered that the Romans transported water in lead pipes more than 2,000 years ago. In fact, Roman smelting of lead and copper ores between 500 and 300 caused a small rise in atmospheric pollution that was recorded in Greenland ice cores. Watch tutorial, Minerals versus Rocks. In addition, some rocks are composed of non-mineral matter. These include the volcanic rocks obsidian and pumice, which are non-crystalline glassy substances, and coal, which consists of solid organic debris. Although this chapter deals primarily with the nature of minerals, keep in mind that most rocks are simply aggregates of minerals. Because the properties of rocks are determined largely by the chemical composition and crystalline structure of the minerals contained within them, we will first consider these earth materials. Concept checks 3.1. 1. List 5 characteristics of a mineral. 2. Based on the definition of mineral, which of the following, gold, liquid water, synthetic diamonds, ice, and wood, are not classified as minerals? 3. Define the term rock. How do rocks differ from minerals? 3.2 Atoms, building blocks of minerals. Compare and contrast the 3 primary particles contained in atoms. When minerals are carefully examined, even under optical microscopes, the innumerable tiny particles of their internal structures are not visible. Nevertheless, scientists have discovered that all matter, including minerals, is composed of minute building blocks called atoms, the smallest particles that cannot be chemically split. Atoms, in turn, contain even smaller particles, protons and neutrons located in a central nucleus that is surrounded by electrons. Figure 3.42 Models of an atom. A. Simplified view of an atom having a central nucleus composed of protons and neutrons, encircled by high-speed electrons. B. This model of an atom shows spherically shaped electron clouds surrounding a central nucleus. The nucleus contains virtually all of the mass of the atom. The remainder of the atom is the space occupied by negatively charged electrons. Properties of protons, neutrons, and electrons. Protons and neutrons are very dense particles with almost identical masses. By contrast, electrons have a negligible mass, about 1/2000 that of a proton. To visualize this difference, imagine a scale on which a proton or neutron has the mass of a baseball, whereas an electron has the mass of a single grain of rice. Both protons and electrons share a fundamental property called electrical charge. Protons have an electrical charge of +1 and electrons have a charge of 1. Neutrons, as the name suggests, have no charge. The charges of protons and electrons are equal in magnitude but opposite in polarity, so when these two particles are paired, the charges cancel each other out. Since matter typically contains equal numbers of positively charged protons and negatively charged electrons, most substances are electrically neutral.
Illustrations sometimes show electrons orbiting the nucleus in a manner that resembles the planets of our solar system orbiting the Sun. However, electrons do not actually behave this way. A more realistic depiction would show electrons as a cloud of negative charges surrounding the nucleus. Studies of the arrangements of electrons show that they move about the nucleus in regions called principal shells, each with an associated energy level. In addition, each shell can hold a specific number of electrons, with the outermost shell generally containing valence electrons. These electrons can be transferred to or shared with other atoms to form chemical bonds. Most of the atoms in the universe were created inside massive stars by nuclear fusion and then released into interstellar space during hot, fiery supernova explosions. As this ejected material cooled, the newly formed nuclei attracted electrons to complete their atomic structure. At the temperatures found at Earth's surface, free atoms generally have a full complement of electrons, one for each proton in the nucleus. Elements, defined by their number of protons. The simplest atoms have only one proton in their nuclei, whereas others have more than 100. The number of protons in the nucleus of an atom, called the atomic number, determines its chemical nature. All atoms with the same number of protons have the same chemical and physical properties. Collectively they constitute an element. There are about 90 naturally occurring elements, and several more have been synthesized in the laboratory. You are probably familiar with the names of many elements, including carbon, nitrogen, and oxygen. All carbon atoms have 6 protons, whereas all nitrogen atoms have 7 protons, and all oxygen atoms have 8. The periodic table, shown in Figure 3.5, is a tool scientists use to organize the known elements. In it, elements with similar properties line up in columns, referred to as groups. Each element is assigned a 1 or a 12-letter symbol. The atomic number and atomic mass for each element are also included in the periodic table. Figure 3.5 Periodic Table of the Elements. Figure 3.5 Full Alternative Text Description. Did you know? The purity of gold is expressed by the number of carats. 24 carats is pure gold. Gold less than 24 carats is an alloy of gold and another metal, usually copper or silver. For example, 14-karat gold contains 14 parts gold mixed with 10 parts of other metals. Atoms of the naturally occurring elements are the basic building blocks of Earth's minerals. Most elements join with other elements to form chemical compounds. Therefore, most minerals are chemical compounds composed of atoms of 2 or more elements. These include the minerals quartz, halite, and calcite caco. However, a few minerals, such as diamonds, sulfur, and native gold and copper, are made entirely of atoms of only one element. Concept checks 3.2. Figure 3.6 Examples of minerals composed of a single element. 1. Make a simple sketch of an atom and label its 3 main particles. Explain how these particles differ from one another. 2. What is the significance of valence electrons? 3.3 Why atoms bond. Distinguish among ionic bonds, covalent bonds, and metallic bonds. Under the temperature and pressure conditions found on Earth, most elements do not occur in the form of individual atoms. Instead, their atoms bond with other atoms. Some atoms bond to form ionic compounds, some form molecules, and still others form metallic substances. Why does this happen? Experiments show that electrical forces hold atoms together and bond them to each other. These electrical attractions lower the total energy of the bonded atoms, and this, in turn, generally makes them more stable. Consequently, atoms that are bonded in compounds tend to be more stable than atoms that are free. The octet rule in chemical bonds. As noted earlier, valence electrons are generally involved in chemical bonding. Figure 3.7 shows a shortened way of representing the number of valence electrons for some selected elements. Notice that the elements in group I have 1 valence electron, those in group 2 have 2 valence electrons, and so on, up to 8 valence electrons in group 8. Each dot represents a valence electron found in the outermost principal shell. Figure 3.7 Full Alternative Text Description. The noble gases have very stable electron arrangements with 8 valence electrons and, therefore, tend to lack chemical reactivity. Many other atoms gain, lose, or share electrons during chemical reactions, ending up with electron arrangements of the noble gases. This observation led to a chemical guideline known as the octet rule. Atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. Although there are exceptions to the octet rule, It is a useful rule of thumb for understanding chemical bonding. Figure 3.7. Diagrams for certain elements. When an atom's outer shell does not contain 8 electrons, it is likely to chemically bond to other atoms to achieve an octet in its outer shell. A chemical bond is a transfer or sharing of electrons that allows each atom to attain a full valence shell of electrons. Some atoms do this by transferring all their valence electrons to other atoms, so that an inner shell becomes the full valence shell. When the valence electrons are transferred between the elements to form ions, the bond is an ionic bond. When the electrons are shared between the atoms, the bond is a covalent bond. When the valence electrons are shared among all the atoms in a substance, the bonding is metallic. Ionic bonds, electrons transferred. Perhaps the easiest type of bond to visualize is the ionic bond, in which one atom gives up one or more valence electrons to another atom to form ions, positively and negatively charged atoms. The atom that loses electrons becomes a positive ion, and the atom that gains electrons becomes a negative ion. Oppositely charged ions are strongly attracted to one another and join to form ionic compounds. Consider the ionic bonding that occurs between sodium and chlorine. To produce the solid ionic compound sodium chloride, the mineral halite. Notice in Figure 3.8a that a sodium atom gives up its single valence electron to chlorine and, as a result, becomes a positively charged sodium ion. Chlorine, on the other hand, gains one electron and becomes a negatively charged chloride ion. We know that ions having unlike charges attract. Thus, an ionic bond is an attraction of oppositely charged ions to one another that produces an electrically neutral ionic compound. Figure 3.8 Full alternative text description. Figure 3.8 Formation of the ionic compound sodium chloride. Figure 3.8b illustrates the arrangement of sodium and chlorine ions and ordinary table salt. Notice that salt consists of alternating sodium and chlorine ions, positioned so that each positive ion is attracted to and surrounded on all sides by negative ions and vice versa. This arrangement maximizes the attraction between ions with opposite charges, while minimizing the repulsion between ions with identical charges. Thus, ionic compounds consist of an orderly arrangement of oppositely charged ions assembled in a definite ratio that provides overall electrical neutrality. The properties of a chemical compound are dramatically different from the properties of the various elements comprising it. For example, sodium is a soft silvery metal that is extremely reactive and poisonous. If you were to consume even a small amount of elemental sodium, you would need immediate medical attention. Chlorine, a green poisonous gas, is so toxic that it was used as a chemical weapon during World War I. Together, however, these elements produce sodium chloride, the harmless flavor enhancer that we call table salt. Thus, when elements combine to form compounds, their properties change significantly. Covalent bonds, electron sharing. Sometimes the forces that hold atoms together cannot be understood on the basis of the attraction of oppositely charged ions. One example is the hydrogen molecule in which the two hydrogen atoms are held together tightly and no ions are present. The strong attractive force that holds two hydrogen atoms together results from a covalent bond, a chemical bond formed by the sharing of one or more valence electrons between a pair of atoms. Imagine two hydrogen atoms approaching one another, as shown in Figure 3.9. Once they meet, the electron configuration changes so that both electrons primarily occupy the space between the atoms. In other words, the two electrons are shared by both hydrogen atoms and are attracted simultaneously by the positive charge of the proton in the nucleus of each atom. In this situation, the hydrogen atoms do not form ions. Instead, the force that holds these atoms together arises from the attraction of oppositely charged particles, positively charged protons in the nuclei and negatively charged electrons that surround these nuclei. When hydrogen atoms bond, the negatively charged electrons are shared by both hydrogen atoms and attracted simultaneously by the positive charge of the proton in the nucleus of each atom. Figure 3.9 Formation of a covalent bond. Figure 3.9 Full alternative text description. Metallic bonds, electrons free to move. A few minerals, such as native gold, silver, and copper, are made entirely of metal atoms packed tightly together in an orderly way. The bonding that holds these atoms together results from each atom contributing its valence electrons to a common pool of electrons, which freely move throughout the entire metallic structure. The contribution of one or more valence electrons leaves an array of positive ions immersed in a sea of valence electrons, as shown in Figure 3.10. Metallic bonding is the result of each atom contributing its valence electrons to a common pool of electrons that are free to move throughout the entire metallic structure. The attraction